In Chapter 21, we're going to be looking at substitution reactions that occur on carbonyl compounds, but we're going to be looking specifically at those substitution reactions that occur at the alpha carbon. In previous chapters, when we've talked about carbonyl compounds, we've mainly focused on reactions that occur directly at the carbonyl, either nucleophilic addition, which we saw with aldehydes and ketones back in chapter 18, or with nucleophilic acyl substitution, which we saw with acid derivatives, carboxylic acid derivatives, and we saw that in chapters 19 and 20. And we looked actually at both of these all the way back in chapter 17. Well, now what we want to do is we want to look at what happens when we do reactions at the alpha carbon. It's a whole different set of reactions that we can do. So we'll start by looking at what kinds of reactions they can undergo, and we also want to look at how they undergo those reactions. So there's two possibilities as far as doing reactions that are at the alpha carbon. We can have a aldehyde or ketone or some sort of carbonyl compound that has an alpha hydrogen. We can have it react as an enol. We talked about enols previously. We're going to talk about them some more. But we can also have them where we deprotonate the hydrogen and turn it into an enolate. And with either of those, we can have those react with electrophiles. So either way, these reagents are going to act as nucleophiles. So when we start doing reactions with enols and enolates, we're going to think of them as nucleophiles. Let's start with enols because we have talked about enols before. We remember that way back when we talked about alkynes in chapter 11, we did two reactions, one where we did hydration across the carbon-carbon triple bond. When we did hydration, we ended up forming an enol that tautomerized into a ketone. And then also in chapter 11, we did hydroboration followed by oxidation that did anti-Markovnikov addition on a terminal alkyne and gave us an enol that tautomerized into an aldehyde. And just as a reminder, these are tautomers. Tautomers are constitutional isomers that are in equilibrium with each other. So these are tautomers, and they're constitutional isomers, so they are different substances, but they are in equilibrium with each other. When we look at what the position of equilibrium is, it's going to greatly depend on what things are attached to the carbonyl. So we'll find that for most compounds, aldehydes, ketones, any of those, that if we have an enol, that the equilibrium is going to favor the keto form. The reason for this is that our carbonyl group, the carbon-oxygen double bond, is much stronger than the carbon-carbon double bond. So energetically, it's going to favor the keto form. And less than 1%, generally speaking, is going to form for the enol form. And we'll find that even for this one with this unsymmetrical ketone, we do have two possibilities to form for the enol, but the sum of those is still less than 1%. So it's a very small percentage. We do have another possibility, and that's where we have 1,3-dicarbonyl compounds, or sometimes we'll refer to these as beta-carbonyl compounds. So beta-carbonyl, the beta carbon is the number 3 carbon, and so here is an example of a beta-dicarbonyl compound. That beta-dicarbonyl compound, the 2,4-dione, so pentane 2,4-dione. Here, if we count one of these as the alphas, or one of these as the first position, and then this is the alpha carbon, and that's the beta carbon. So on that beta carbon, we do have that carbonyl, and that makes it possible to have more of the enol form. What we'll find is that with a lot of these types of compounds, the enol form is going to be there in a greater amount than even the keto form, where both of them are fully formed carbonyls. We'll see that there's two factors that will make this possible. Why is it that we get these? Why is it that we get these versus the keto form when we're dealing with the dicarbonyl compounds versus the aldehydes and ketones we saw on the previous page? Well, two main factors are at play here. Conjugation, as we can see, we've got an alpha-beta unsaturated carbonyl compound. So we have an unsaturation there. Conjugation provides extra stability. So that's one factor. And the second factor is this intramolecular hydrogen bonding. And it's true for both of these enol tautomers. Now, these enol tautomers happen to be the same thing, but they are in equilibrium with each other, where the double bond is moving back and forth, and the double bond between the oxygens is moving back and forth, and even the hydrogen is moving back and forth. So that is intramolecular hydrogen bonding, helps to contribute to this enol form. Now, there are two ways of doing tautomerization from the enol form to the keto form, or vice versa, from the keto form to the enol form. And those two methods are going to be acid-catalyzed and base-catalyzed. So let's look at the acid-catalyzed mechanism first. So when we have acid-catalyzed tautomerization, we protonate as our first step. We'll protonate the carbonyl group. That will give us a resonance stabilized carbocation. It puts a positive charge on that carbon. And then we deprotonate the alpha carbon to give the enol. It can easily go back the other way. Here we can protonate this and then deprotonate this to get back to the keto form. So when we're doing acid catalyzed, it's always protonation, then deprotonation when we're going between one form and another. With base-catalyzed tautomerization, it's exactly the opposite. With base-catalyzed, we're going to deprotonate first, and then we'll protonate. So when we deprotonate, we'll deprotonate that alpha, the alpha carbon to give a carbanion. So we'll have a resonance stabilized carbanion. This is the enolate form. And then that enolate, we'll get the other resonance structure, puts the negative charge on the oxygen. We can then protonate that oxygen to give the enol. Either way, we get the enol. So, and it doesn't take a lot of either the acid or a base to do this equilibrium process. So let's look at potential reactions with enols. So enols are electron rich. So since they are electron rich, they will react with electrophiles. They will act as nucleophiles. They are more electron rich than alkenes because the oxygen group is a powerful resonance donating effect. And as a consequence, we can draw two resonance structures for the enol. This is our additional resonance structure, and it puts a negative charge on that carbon. And so that means the average structure has a partial negative charge on the carbon, and it makes it so that that carbon is electron rich. That electron-rich carbon can react with an electrophile. We will look at a variety of electrophiles in this chapter that we can do reactions on. So let's look at this very first one, and this first one is pretty simple. So this is a pretty straightforward problem. Make sure I've got this lined up here. All right, and so here we want to draw the enol or keto tautomers of each compound. So if we have the enol, we want to draw the keto form, and if we have the keto form, we want to draw the enol form. So in this case, we have the enol, so we want to draw this as a keto. This is a very easy process to do. Just find where the oxygen is, and if it's an enol form, make that the carbonyl, get rid of the carbon-carbon double bond, and if it's the other way around, where we have the carbonyl, find a carbon with an alpha hydrogen and put the double bond there, and we'll make the enol form. So here we'll just do enol. So this aldehyde only has one type of beta or alpha hydrogen, so we're only going to get one enol. All right, so that would be our enol there. On this one, we've got two different types of beta hydrogens. We have the beta hydrogens that are adjacent to this phenyl group, and we also have the beta hydrogens that are out here on this ethyl group. So we're going to draw both of those. So I'm just going to put C6H5 rather than draw out the whole thing. But that is a phenyl group, so you just draw a benzene ring there. We'll do a double bond here. Let's try that again. There's a double bond there, OH. And then we have another resonance structure, C6H5. And we can have a double bond there. And so those are our two, going to be our two enol forms. All right, that one got a little messy. Sorry about that, but hopefully you can see what's going on there. This one's easy because we have the enol and we want to draw the keto form. So we just turn that into a carbonyl. So we'll get that. We will get that ketone, that cyclic ketone. All right, I paused it and kind of cleaned up that structure a little bit. So I wasn't satisfied with what I had drawn. I suppose I could have cleaned this one up, but there you go. All right, here we can also do the enol form on esters. So here we've got an ester. We can't do the enol over here because there's an oxygen, but we can put the carbon-carbon double bond here. So we can draw that enol. All right, and we will get that carbon-carbon double bond there for our enol. On this one, we've got a beta dicarbonyl compound, and since this is a beta dicarbonyl compound, we can get two enol forms. One where the OH is on this carbon, and one where the OH is on the other carbonyl. So one where the OH is on this oxygen, one where it's on this oxygen. So we are going to draw both of those. So we'll get the double bond there and the keto form there. And then we can also get the other one. Have to go a little smaller here, but one, two. And we'll put the double bond here. And I'm going to go ahead and draw it so the hydrogen bonding is kind of obvious there. So we can get that enol. All right. You could conceivably draw an enol form where you put a double bond here. However, that is going to be higher in energy and less likely to be formed than these enols that we have for the beta carbonyl compounds. So these are going to be the primary enols that are formed. So now let's look at enolates. Enolates are sort of the companion to enols. They're a little bit different. Instead of just doing a tautomerization, we're actually going to deprotonate the alpha carbonyl or the alpha carbon with some base. It's just some sufficiently strong base. We'll talk about those bases here in just a moment. But we're going to deprotonate it, and when we do, we'll get a negative charge on that carbon, but we can do resonance stabilization where we move the charge around and move the double bonds around, and that puts the negative charge on the oxygen. Because we have one of our resonance structures that has the negative charge on the oxygen, that means this is pretty stable compared to other carbon hydrogens. And so that means, since this is pretty stable, this hydrogen is going to be more acidic than your typical sp3 hybridized carbon. So again, this is going to be more stable because our conjugate base has two resonance structures, and one of those resonance structures puts the negative charge on an oxygen. How stable? How acidic? I'm glad you asked. Let's look at a comparison of pKa values for different sp3 hybridized carbon containing compounds. So we're going to start all the way up here. This one is just ethane. Ethane has nothing to stabilize it. When you try to deprotonate it, you're going to get this CH3CH2 minus. This is a very, very strong base. There's nothing to stabilize it, and as a consequence, this has a very high pKa. So that's one of our strongest bases possible. If you just have a straight up alkane, that's going to be a super strong base. Now let's look at this one. Here we've got an allylic carbon hydrogen, and when we deprotonate that, we will get these resonance structures to form this allylic carbanion. And the resonance structures do help. It makes it more stable than our alkane up here to be deprotonated, but you'll still see that pKa of 43, that's really high. So that means this is an extremely weak base, and these are extremely strong. This is a really weak acid, and these are extremely strong bases. For aldehyde, for a ketone, we're going to start with acetone. Aldehydes are a little bit lower than the ketone, and we'll talk about why that is in a few minutes. But here with this ketone, acetone, it has a pKa of about 19, and the reason it's so low is because it has one of the resonance structures that puts a negative charge on the oxygen. And that resonance structure with the negative charge on the oxygen is very stable relative to the one where it's on the carbon. And so that helps to lower, helps to make this more stable and helps to lower the pKa. In other words, make this more acidic. Now, if we compare this to oxygen acids like ethanol, again, we don't normally think of ethanol as an acid, but in organic chemistry, we've seen it as an acid many times. So when we deprotonate that, we get the ethoxide. There aren't any resonance structures, but it does put the full negative charge on an oxygen atom. So this is going to be more stable. This anion is going to be more stable than our enolate that we had up here, but not a whole lot, just a little bit. So for an sp3 hybridized carbon, that's a pretty low pKa, making this fairly acidic in organic chemistry terms. All right, here we've got a relatively strong organic acid, carboxylic acids. We talked about this back in chapter 19 quite a bit. And because we've got two resonance structures and they each put the negative charge on the oxygen, that's a pretty stable anion, which means this is a relatively strong acid. Now, it's not as strong as like a regular strong acid like HCl or sulfuric acid, but it is a reasonably strong acid. All right, so 19. Let's look at an electron density map of the acetone enolate. That's the one we just looked at, this one. So the acetone enolate, and compare that to an isopropoxide anion. So the acetone enolate, when we deprotonate the carbonyl, we'll get some partial negative charge on the carbon and some partial negative charge on the oxygen. When we look at this electron density map, we will see that we get more of the negative charge on the oxygen. That makes sense. Oxygen's more electronegative. We should expect it there. But you'll see that there is some negative charge because it's not very blue. There's some negative charge here on the carbon. If we look at the alkoxide, and this one is isopropanol, the conjugate base of isopropanol, so it's isopropoxide. And when we deprotonate it, all of that negative charge stays on the oxygen. There's no way to delocalize that negative charge to other atoms. And because of that, this is this is a relatively strong base. But one thing I want you to keep in mind that this is still a weaker base than this acetone enolate. For isopropoxide, it's going to be somewhere in the range of 16, 17 for the pKa of the isopropyl alcohol. So this will not be quite as strong as a base as the acetone, the conjugate base of acetone. Acetone has the pKa of around 19. So 19 versus 18. They're pretty close, but this one is a little bit less basic. All right. The reason for that is that all of the negative charge is on oxygen, rather than attempting to delocalize it to a carbon, which is not as electronegative. We've got it all on the most electronegative atom. All right. So that gives you an idea of where the difference in those negative charges are. This negative charge on the carbon, or at least that partial negative charge on the carbon, is key to the reactivity of enolates. So now let's look at enolates and other related anions. So it is possible to form enolates with compounds other than aldehydes and ketones. You can do it with esters. So if you deprotonate the alpha carbon on an ester, you can delocalize the negative charge that's on the carbon to the oxygen. So we'll get a resonance stabilized enolate here as well. Now this one is not quite as acidic as the ketone. The ketone had a pKa of about 19. This one has a pKa of about 25. The reason it has that pKa of about 25 is that this oxygen donates a significant amount of electron density, making this less stabilizing than it does with the ketone. Here with the nitrile, we'll also see a pKa of about 25. So that's going to be not quite as acidic as the acetone. We do get a resonance structure that puts negative charge on the more electronegative atom, but you'll notice it's on a nitrogen, and nitrogen is not quite as electronegative as oxygen. When we have the alpha beta dicarbonyl compounds, or not the alpha beta, the 1,3 dicarbonyl or beta dicarbonyl compounds, it's easier to deprotonate. So here we've got a diketone. So it's a 1,3 diketone, and specifically it's pentane 2,4-dione. So the 2 position and the 4 position, and they're beta to each other, we've got two ketone functional groups, 2 carbonyls. Well, when the base comes in and deprotonates that, we've got 3 resonance structures we can draw for this particular enolate. One, where the negative charge is on the carbon. That, of course. We also have the possibility of putting the negative charge on the first oxygen, and we could also put the negative charge on the second oxygen. And so these are just resonance structures of each other. That means that we're now delocalizing that negative charge to 2 different oxygens and the carbon. And that's going to be more stable than just delocalizing it to 1 oxygen and the carbon. As a result, you'll see here the pKa of this diketone is about 9. That's really, really low. So that is more acidic than phenol. So it's more acidic than phenol. That's kind of amazing. All right, here are a few more of our carbonyl and dicarbonyl compounds. Amides, they have to be tertiary amides. If you have a secondary or primary amides, the hydrogens on the nitrogen end up being more acidic than our alpha carbons, and so that messes up our measurement. But here we're going to find that these have a pKa of about 30. Nitriles and esters, we mentioned those were about 25. If you have a ketone, usually falls in at about 19. Aldehydes, because we have less electron density added with the hydrogen than we do with the methyl, that one has a pKa all the way down at 17. That's pretty low. All right, for our dicarbonyl compounds, they get even lower. So for this 1,3 diester, it's about 13. All right, if you have a 1,3 dinitrile, it's at about 11. A beta keto ester, that's where one is an ester and one is a ketone. That one's at about 11 as well. So the more of the ester groups you have, the higher the pKa is going to be. It's going to be a little bit less acidic. And if you go to keto form, like ketos instead of esters, it's going to cause them to go down. And here is that diketone that was at 9. Presumably, if you had the dialdehyde, it would have a slightly lower pKa, but I don't know what the pKa of that is. All right, so here we go, 21.7. All right, so I just looked it up before going to the in-class assignment problem. If you have this as the 1,3-propane dial, so you have it as a dialdehyde, has a pKa a little bit below 7. It's about 6.8, 6.7, 6.8. Pretty acidic. That is a pretty acidic compound. All right, so let's look at number 7 on the in-class assignment. That second one on that first page. So we're going to go to our document camera here. All right, rank the protons labeled in the CH2 groups in order of increasing acidity. So from least basic to the most basic. Well, the least basic is going to be this one. And the reason that one's going to be the least basic, all right, so this one is going to be the least basic, is because when you deprotonate it, there's nothing really there to stabilize. So we would expect the pKa of that particular hydrogen to be somewhere in the 40s, maybe even 50. It's going to be pretty high. And in fact, all of these other hydrogens that are on there are going to be more acidic, so it would be very difficult to even measure what the pKa of this hydrogen is. All right, on this one, and you can just barely see that it's highlighted here, but on this one, that one's going to be more acidic because it does have a carbonyl, so you could form an enolate. All right, so this one is going to be more acidic than these. We would expect a pKa, because it is a ketone, we're going to expect a pKa somewhere around 19 for that one. All right, and then when we go to this one, we've got a dicarbonyl. And so that particular one with that dicarbonyl, we're going to expect a pKa of about 9. So again, this one, I don't know exactly what it is, but it's probably going to be in the 40s somewhere. So somewhere in the 40s. All right, this one we would expect somewhere at around 19 because it's a ketone. And this one we would expect somewhere at around 9. In fact, that one is very close to 9 because we know that particular one is about 9. So, so this would be most acidic, and that would be the least acidic. Okay. What about the equilibrium position of enolate formation? So what is going to be our equilibrium position? Well, it's going to depend on what is our starting carbonyl, and it's going to depend on how strong is our base. So let's start with an example where we have a carbonyl compound that has a pKa of around 20. That's about what you would expect for just a normal ketone. So it's around 20. You know, we saw one that was 19, but all right, we'll just say around 20. If we have a base, how strong of a base do we need so that we get more of this enolate than we do of our starting carbonyl compound? Well, we can predict that by looking at the pKa of this acid and the pKa of the conjugate acid. The higher this pKa is, that means the weaker that conjugate acid is as an acid. So the weaker this is as an acid, the stronger this is as a base. So if we can get a higher pKa for the conjugate acid of our base than the pKa of our carbonyl compound, then we should get mostly our product, or at least a significant percentage of it will be in the enolate form. So just look at the pKa's and compare them. So let's look at this. So we're going to start with our assumption that we've got one that has a pKa of around 20. And so with a pKa of around 20, we could look at hydroxide. The conjugate acid of hydroxide is H2O, which has a pKa close to 16, 15.7, but 16 is close enough there. Well, with this at 16 and that at 20, we're going to have almost all of it will be in the form of the keto. So this one is going to lie far to the left. Less than 1% is going to be in the form of the enolate. If we go with an alkoxide like ethoxide, well, the conjugate acid of ethoxide is ethanol. Ethanol also has a pKa at around 16. Again, less than 1% of this reaction is going to be in the enolate form. If we go with a slightly stronger alkoxide, so this is potassium tert-butoxide, one of my favorite strong sterically hindered bases. Its conjugate acid is tert-butanol, and with tert-butanol, that has a pKa of 18. We're going to find our percentage enolate jumps up to several percent. All right, so several percent. And then if we go to very strong bases, so sodium hydride, its conjugate acid is H2, which has a pKa of around 35. That with that number, 35 versus 20, it's going to be essentially 100% in the form of the enolate. And in addition to this, when you use this, you will have the hydrogen just bubble right out of solution, so you won't really get an equilibrium. Once it reacts, it'll stay there. And then this is one here. This one is lithium diisopropylamide. All right, and we're going to talk a lot about this one. We call this one LDA for short. We're going to talk about it on the next page. The conjugate acid is not the lithium, but it's just the diisopropylamine. That hydrogen has a pKa of around 40, which means that this is a really strong base. At 40, again, essentially 100% of our reaction is going to be in the form of the enolate. So we will deprotonate that carbonyl essentially 100%. Now, sometimes you want 100%, and sometimes you don't. Sometimes you only want a few percentage points. And I will explain why that is coming up here in just a bit. Now, if we had picked a stronger acid as our carbonyl compound, so if we had picked any of those beta dicarbonyls, all of these would deprotonate to essentially 100%. So how much deprotonates is going to depend on, which carbonyl compound you choose and also which base you choose. So just compare. If the pKa of the conjugate acid of your base is more than, 1 or 2 pKa units greater than the pKa of your carbonyl compound, you're going to get mostly deprotonated and mostly in the enolate form. All right, let's look a little bit closer at lithium diisopropylamide. So lithium diisopropylamide, or LDA. Again, this is one of those where a lot of chemists will call this lithium diisopropylamide. There's nothing wrong with that. In fact, probably more people call it that than amide. Just heads up in case you run into somebody else, so they won't think you're some, backwards chemistry professor from Texas. There you go. All right, so again, that LDA, as we call it for short, is very effective at deprotonating our alpha hydrogens on carbonyl compounds. And so if we want essentially 100%, LDA is a pretty good bet. Now, the downside of LDA is that you do need to kind of know what you're doing to handle it. It's very, very reactive. It's water sensitive. If you leave it out in moist air, it will absorb moisture from the air and get converted into its conjugate acid. So this is not something to mess around with. And it's also kind of expensive. I was looking it up, and if you want to get a 25-gram bottle of this, you can get it for the low cost of $317 from Sigma Aldrich. Now, you can get bigger bottles that are better per gram, but that, that's a pretty significant outlay for a reagent, compared to other common reagents that we use, common bases. So if you need it, it's worth it. But if you can use something else, sometimes the something else might be a more favorable reaction. Now, so LDA, because these two isopropyl groups are pretty bulky, it makes this a non-nucleophilic nitrogen. So we'll find that LDA is a very strong non-nucleophilic base. So it fits in that category. At negative 78 degrees Celsius, you can take cyclohexanone and deprotonate essentially 100% of those alpha hydrogens to give you this. And if you're wondering, how do I get to negative 78? Well, it just so happens that the sublimation point for dry ice, which is just solid carbon dioxide, sublimation point for that is negative 78.5. So if you mix dry ice with a solvent, typically solvent you might use would be acetone or isopropyl alcohol or some other solvent that's a good heat transfer fluid. You can use that as a bath and you can get your reaction down to negative 78. So dry ice is the answer there. You wouldn't put the dry ice directly into the reaction, but you could put the dry ice in a container and then put your flask into that dry ice. All right, so there is the reaction. So how do you form LDA? Let's say you don't want to buy LDA from Sigma Aldrich for $317 for a 25 gram sample. Let's say you want to make it. Well, you can make it. You can make it if you use the lithium diisopropylamine as your starting material, but you need an even stronger base to deprotonate it. So the stronger base is going to be something like butyllithium. So you can use butyllithium to convert the lithium diisopropylamine to LDA, but also that butyllithium, it's not free either. So all of these have some cost and they take some effort to store and handle properly. So, but this is one of our strongest bases known. And you might think, well, why don't we just use this? Well, this is an organolithium reagent, and we couldn't use it to deprotonate because it's also a really good nucleophile. So whether you would get deprotonation or nucleophilic attack, it depends, but you probably get the nucleophilic attack. All right, so now let's look at some reactions with enolates. Now that we've seen how it is that we form enolates, what are the bases we can use, let's look at some reactions that we can do with enolates. So enolates, first of all, let's talk about what the enolate is. We have the resonance stabilized form of that enolate that puts some negative charge on the carbon and some negative charge on the oxygen. Because that bottom one is a better structure, there's probably more negative charge on the oxygen than there is on the carbon. However, we're going to find, and when we have that, that means both of those spots could potentially be nucleophilic. We could have a nucleophilic oxygen or nucleophilic carbon. However, and we call that an ambident nucleophile. So ambident just means it's in two places. However, and I keep saying this, however, the preferred pathway on this is going to be where the electrophile reacts with the carbon. There are some very specific reagents that might react with that oxygen, but most of the things we're going to be looking at will react with the carbon as an electrophile. So let's get to business here. Let's do enolates of unsymmetrical carbonyls. So we're going to start with unsymmetrical carbonyls. And we're going to take 2-methyl cyclohexanane. Well, there's two potential places that we could deprotonate 2-methyl cyclohexanone. We could deprotonate at the 2 position. Let's see. No, at the 6 position here. If we deprotonate at the 6 position, then that's a secondary hydrogen that's going to be a little bit easier to remove than the tertiary hydrogen, but because it is less sterically hindered, but we're also going to find that it's not quite as stable as the other one. So when we deprotonate here, this is our kinetic enolate. So this will form faster because it is less sterically hindered. If we want to deprotonate at the 2 position where we have the methyl already, that methyl is going to, or that hydrogen, when we deprotonate it, we'll get this, and then our enolate, our resonance structure for the enolate, gets a more substituted alkene. Well, that means that this enolate is more stable than this one. So we've talked about kinetic versus thermodynamic before. And so the kinetic forms more easily, but the thermodynamic forms at sort of equilibrium conditions. Well, the way that we typically get kinetic products is by going at low temperature. And the way we typically get the thermodynamic product is by doing it at higher temperature. And the higher temperature is usually room temperature. All right, so the conditions that will favor the kinetic enolate. First, if we pick a very strong non-nucleophilic bulky base like LDA, that's going to help us to get the enolate to form really, really fast. So it will come along and get the least sterically hindered hydrogen, and it will form it very, very quickly. So if we use LDA, we can deprotonate that less sterically hindered carbon, and we can do it very quickly. The other conditions are going to be to use a polar aprotic solvent like tetrahydrofuran. Tetrahydrofuran is, we've talked about this before, but it is an ether that's more polar than diethyl ether. And so that allows for a polar protic environment. So there, it's possible to dissolve both your starting materials, which is a little bit polar, and your products, your intermediates here, which are ionic, which are pretty darn polar. So we need something polar. We can't go with completely nonpolar, otherwise this comes right out of solution. So we need something polar, but we don't want anything protic. Protic is going to lead to thermodynamic product. The final thing is this low temperature. And as I mentioned before, if you want to get negative 78, a really good choice for that is going to be to use dry ice as your cooling agent, because it's right at negative 78.5, and you mix it in with a solvent like acetone, you can make a nice acetone dry ice bath, and this will work great. Okay, low temperature is typically ideal. We've seen this before. If you want to go low temperature, if you want the kinetic, you go low temperature. Now, conditions that favored the thermodynamic enolate. We still want a strong base, but we don't want one that's as strong as LDA. And so we're typically going to use an alkoxide, and there's a couple of different options that we like. And we typically will use a polar protic solvent, like an alcohol. Now, if you have an alkoxide and an alcohol, your best choice is going to be to use the solvent that is the conjugate acid of that alkoxide. So for example, if you want to use the base sodium ethoxide, the best solvent for that is going to be ethanol. If you want to use potassium tert-butoxide, the best solvent for that is probably going to be tert-butanol. So it helps if these match. Other conditions that we're going to have, so polar protic solvent, a strong base but not as strong as LDA, and then our final conditions that we typically want are going to be around room temperature. If you go to really low temperature, you can do kinetic, but at room temperature, you're more likely to form our thermodynamic product. So let's look at number 36 on our in-class assignment. Number 36 here, and switch over. What is the major enolate or carbanion that is formed when each compound is treated with LDA? So when each is treated with LDA. So I'm just going to show the carbanion. You can draw the resonance structure where you delocalize to the oxygen, but I'm just going to show the carbon anion. And with LDA, we're going to assume that we're going to do this at low temperature to get our whatever our kinetic product is. On some of these, kinetic doesn't matter because there's only one choice. But on this one, we have two different types of hydrogens. And if we're using LDA, we're going for the kinetic, which is going to be the less substituted. So when we deprotonate that, we're going to get the negative charge on that methyl of this methyl ketone. So we'll get we'll deprotonate there. That will be our kinetic deprotonating site. On this one, we've got the cyano group. Cyano groups act a lot like the carbonyls, not quite as acidic as the ketone. Ketones, remember, have a pKa close to about 19. This one has a pKa close to 25. But LDA is a strong enough base that we can deprotonate this without any trouble. So cyano, and we will get that. All right, on this one, we've got two choices here, and I'm going to circle these in green so that it's not too bright. We've got two choices there, for those two choices, one of them will be a thermodynamic and one will be kinetic. Since we're using LDA, LDA is going to give us our kinetic, which is going to be our less substituted carbon. So we should expect to put the anion there. We have a cyclohexyl, another cyclohexyl, and then a methyl here, and we would put our negative charge there. So that's where we would deprotonate. If we used a thermodynamic conditions like alkoxide with ethanol or alkoxide with the alcohol and at room temperature, we would get this one, but because it's LDA, we're going to get this one. All right, our final one here, we've got a beta-dicarbonyl, and there is a hydrogen there. And because this hydrogen is so much more acidic than these hydrogens, we're going to deprotonate here. So when we deprotonate, put the negative there. And we'll be able to draw two additional resonance structures for this, one where the negative goes on this oxygen, one where it goes on that oxygen. Okay, so let's look at this next thing. So we're going to look at racemization of the alpha carbon. We've talked about racemization an awful lot. And that's because it's important when we're dealing with stereochemistry to pay attention to when are we going to get racemization. Well, if we have a stereogenic center where we deprotonate, well, when we deprotonate that stereogenic center, we're going to create an sp2 hybridized carbon. The reason for that is that this enolate is resonance stabilized. And if it's resonance stabilized, the only way that we can do resonance stabilization if it's in the same hybridization, and the electrons that we're going to delocalize have to be in a p orbital. So since they have to be in a p orbital, this carbon has to be sp2 hybridized. And so if we had a stereogenic center at that carbon, it is going to be gone because the sp2 cannot be a stereogenic center. So let's see how this applies. All right, so here we've got an example of an alpha carbon that is a stereogenic center. So this alpha carbon doesn't have any hydrogens, but it's already sp2 hybridized. But this one has a stereogenic center, so it has a particular stereochemistry, and so it is chiral. When we deprotonate this hydrogen that's on that stereogenic center, we're going to create an sp2 hybridized carbon, alpha carbon, that will no longer be chiral. So we will have an achiral, enolate. And I've mentioned this so many times. If you have an achiral starting material or achiral intermediate, then you're going to have either an achiral product or a racemic mixture of those products. So if you have this and you deprotonate, then when you come back and you protonate with water, you're going to get a mixture. So you're going to get racemization of that alpha carbon. So that's something you have to be aware of, because if you've invested a lot of time and money and many months of your life doing the research, you don't want to throw away a perfectly good stereogenic center by doing something simple like putting it in aqueous base. That could totally mess it up. All right, we're going to have a very quick preview, and then after this preview, that will be the end of this particular video, and then in the next video, we will do the rest of the chapter. So this preview is going to tell us what's coming up. There's two main types of reactions that we do at the alpha carbon. And one of them is where we take our enolate and react it with electrophiles to do substitution products. And typically, we're going to react it with things like alkyl halides and do an SN2 reaction to get new alkyl groups on that alpha carbon. And we can do this with halogenation, which is not SN2, it's a different kind of reaction. But we can do it with alkyl halides, and it will be alkylation, that'll be an SN2. Either of these, again, are going to involve direct reaction with that, either a carbon or a halogen to give you substitution. The other type that we're going to talk about in this chapter is where we react and actually we talk about this more in the next chapter, but where we react the enolate with other carbonyl groups. And so here we form an enolate, and then if there's some other carbonyl group that's present in solution, that enolate can react with that carbonyl and we'll form our tetrahedral intermediate. And so this is where we take the enolate and we do nucleophilic addition. Or in some cases, we can do nucleophilic substitution. And as I mentioned, we're going to talk about this a lot in chapter 22, which is the next chapter. All right, so that's the end of the first video for chapter 21. In the second video, we're going to look at halogenation. So we're going to look at this very first thing.